Data hazard. Data hazards are caused by data dependencies. Consider the same five-stage MIPS pipeline architecture that we had discussed in the previous video, and consider the execution of these two instructions. Suppose in our first clock cycle, we are fetching this instruction. In the next clock cycle, we can decode this instruction and the operands will be loaded from the registers. Let these be the initial values or the current values of all these registers. In the second clock cycle, we will decode this instruction and the operands are loaded from the registers. In the next clock cycle, we will execute the add operation and the sum or the result will be available. The memory stage is idle and this result will be written to the register R1 only at the end of the write back stage at the end of the fifth clock cycle. Now in clock cycle 2, while this instruction is in the decode stage, our fetch unit is free, hence we can start fetching the next instruction. In the next clock cycle, if we try to decode this instruction, decoding the instruction also involves loading the operands from the register. Hence, we will load these operands or these values from the registers R1 and R5. But according to the normal program order, what the programmer expected is a value of 15 in the register R1, but that value 15 is not yet written to the register R1. So this data will be written to the register R1 only at the end of the fifth clock cycle, and in the third clock cycle itself, we are trying to access that data from the register R1. Means the execution of one instruction is dependent on the data produced by some previous instruction and that data is not yet available, and this kind of data dependency leads to a hazard or conflict called data hazard. And here the hazard is caused because we are trying to read some data which is not yet written. So what is the solution? The simplest solution is to stall the pipeline. Here we are expected to read the data from the register R1 only once it is written at the end of the fifth clock cycle. So we'll wait till the fifth clock cycle and decode the next instruction only at the sixth clock cycle. In other words, we stall the pipeline and decode the instruction in the sixth clock cycle. By that time, both the result will be available in the register, both the operands can be loaded from the register, can be executed, and this result will be written to the register R4 at the end of the write back stage at the end of the 9 clock cycle. The stall in the pipeline leads to correct program execution, but here we can see we get this instruction out in the 5th clock cycle and we get the next instruction out in the at the end of the 9th clock cycle. Hence, it leads to the wastage of CPU cycles and leads to low performance of the pipeline. This pipeline stalling can avoid data hazard, but it leads to low performance of pipelining. So how can we avoid data hazard without stalling the pipeline? One prominent solution used for solving data hazard is operand forwarding. Here, the problem occurs because in clock cycle 3, while we decode our instruction I2, we are trying to read some data from the register R1, but our required data is not available within that register. Means we are trying to read some data from the register file and that data is not available within the register file. So, whether that data is available somewhere within the pipeline, and that data is required by the instruction I2 at least at the beginning of the execution stage or at the end of the decode stage. And when I2 is at the end of the decode stage, our instruction I1 is at the end of the execute stage, means the sum of the content of R2 and R3 is already computed and is available with I1, but it is not yet written to the register R1. So in the next clock cycle, when instruction I1 moves to the memory stage along with this data, at the same time, if this data can also be forwarded to the input of the execution unit, then I1 who is in the execution unit in the fourth clock cycle can make use of this data for its computation and hence will be able to be executed without causing data hazard and producing the next instruction out in the next clock cycle itself. Means in clock cycle 1 we fetch our first instruction I1. In clock 2 I1 moves to the decode stage and I2 the sub instruction will be fetched. And in clock 3, I1 moves to the execution stage, I2 is being decoded, and some other instruction which is not dependent on all this can be fetched. So here, even though the data is not available within the register, this instruction will be decoded. And by that time, our instruction I1 compute the sum of the content of R2 and R3. So in the next clock cycle, when instruction I1 moves to the memory stage along with this data, if this data can also be forwarded to the input of the execution unit, in the next cycle or in clock 4, when I2 reaches the execution stage, it can make use of this data for its computation. So generally it means in the decode stage we try to read the data from the register file. If the data is available within the register file then it's fine. Otherwise, if the data is available somewhere within the pipeline, forward it to where it is needed. Here we need the data at least in the beginning of the execution stage. If the execution phase is over, then there is no use. And when our instruction I2 is at the beginning of the execution phase, our required data was available in the output of the execution unit. So we forwarded the data from the output of the execution unit to the input of the execution unit.